Share my screen on this video. You're welcome, everyone. I should turn the projector on also.
Dr. Thomas.
Yeah.
At my volleyball practice,
Yes.
coaching yesterday, I was asking like the main lady in charge, who we play, because I was like, do we just play each other the whole time, or do we play other churches in the area? And she said that we just play each other. And so I was like, my professor goes to a church who has another.
But they have also like 45 teams, so they play each other too.
Yeah. But now our older group, we only have 2 teams.
Oh.
And so they would be playing each other the whole time.
My son played basketball this year for the first time at kindergarten. It was a kindergarten upward basketball team, but there were only 2 of the teams, kindergarten teams, so they just played each other every week.
Yeah.
What height did it, like, what did they shoot?
It was very, very short.
Yeah. I was just wondering, like, how did it?
Very, very short. I don't know. I don't know what it is.
But I'm gonna be very bored with my teams if they just play each other the whole time.
Who is in charge of it? What's her name?
Abby.
The lady in charge of it in our church, her name is Andrea.
Abby.
Oh, okay. Oh, it doesn't bother me. I can't even see them. I printed it off because yours was so big of a file that it wouldn't allow me to open it on my iPad. No, everybody else's works. What? Why is that so big? Well, my iPad would not download it to look at it. So I just printed it and moved on with my life. Didn't try to figure it out. Just moved on. I don't care. It's done. It does not matter. Okay, so like I said, there were several issues on the homeworks that I want to talk about because you have a test on Thursday with regular induction and like how it should read and stuff. So this one is actually pretty fun. But a lot of you got a chance to be creative, so that was kind of cool. This one I don't think was where there were the most issues, so we'll just move on. This one we'll talk about today. There were a lot of issues on this, so let's talk through this. This is number 2 on the worksheet. So it says that for integers n greater than or equal to 1, this sum, which is the sum of the even integers up to the n even integer, is equal to n squared plus n. Okay, so proving by induction for the base case, let n equal 1, right? You can say like, oh, Marina, this was the thing on yours, I think. It was the way you started your proof was problematic to me. The way that it read was, I did not like it. Some of you have the issue where you jump in and put the things equal, like plugging in stuff to both sides at the same time and saying, look, they're equal. Like, don't just plug them in separately and say they're equal or less than or whatever. Yeah, so if you were doing the summation stuff, that is fine. When you do that here, let's do it here. Right, so this would be the sum from I equals 1 up to k of 2I. That's equal to k squared plus k. And then you're going to look at the, if you're doing summation notation, you're going from I equals 1 to k plus 1 of 2I. Now, again, in the summation notation, this thing is going to be equivalent to going from I equals 1 to k, and then the k plus first even integer. So you're going to go 2 times k plus 1, right? That's the, like, if you split that sum into 2 pieces, those are the 2 pieces, right?
guy, your issue, was actually like saying a thing. You just had like one half of that, which you can't use, right? So when you do your inductive hypothesis, it needs to be like, hey, this works at the kth step, right? So the sum of the first k even integers is actually k squared plus k. So it does want to pick k step. And then look at the k plus first step. You're going to use the inductive hypothesis for this part. And so you use the fact that that's equal to k squared plus k, and then do some arithmetic to make this actually look like k plus 1 squared plus k plus 1. Right? Yeah. Yeah. This final thing. Yep. When you do the base case, you're replacing n with your first number, right? When you do the inductive hypothesis, you're making it look like the thing, but the n is k now. And when you do the final thing, the like actual like inductive step, you show it works when n is equal to k plus 1. So it should look like the original, but with k plus 1s instead of n's. Yeah. That was a pretty consistent problem also for not just you, Karina, but so yeah, you want to go all the way back to making it look like the original. So, but instead of instead of n's, we have k plus 1s now. And that's how you say, look, the inductive step holds, right? Like this works. Hey, this looks like the same thing, but with k plus 1s instead of n's. This works when n equals k plus 1. That's the point. Yeah. Does that make sense, Ruth? Because that was the same thing you were doing too.
Yeah. Because like I was only getting like half of that. And others were like, yeah, just work from your want to show, and then get your want to show that look like the thing done.
Right.
Okay,
And you are, because once your want to show looks like your thing, you're going to copy your want to show in reverse order to make it look like, yeah, the thing with the k plus 1.
okay, that makes sense.
This is the same, the like analogous idea here for you would be like pre-cal when you're doing your pre-cal proofs, you know, you're verifying identities and you would prove like the left-hand side and you get stuck and you would move to the right-hand side. If you had a teacher that was like, you may only work one side, you know what, all you do is take these things and put them in reverse order down here. It's the, like, you're manipulating the process, right? Like, you would work this side till you got stuck, and then you work this side till it looks the same.
That's what I was doing, and then,
Right.
like, I would stop.
But the extra step is now you need to flip the order of these and write them down.
Right, because you weren't.
Correct. Right. Yep. Okay. There was this one. Most of you did really well on this. I think this is pretty messy. The summation notation on this one is maybe nicer looking than this. I don't know. This is also in Zoom, y'all, so you don't have to take pictures. You can watch it later. Oh, you're welcome to take pictures. I'm not criticizing, but it will be in Zoom. I am recording myself right now. Yes, sir. You can go, so they're all, I've been uploading them in YouTube right after they are done. So you go to my YouTube channel, which is linked in our Blackboard course. Or you click the Zoom meetings link in Blackboard, and at the top, it has 3 like tabs, and one of them is cloud recordings. If you click on that, it has all of our Zoom stuff. Okay, so again, this one was weird. The 3i minus 2 thing. Whitney did this. She like figured out what of those was, and it looked a lot nicer. It was like 1 and 4 and 7, and looked pretty than mine. But anyway, you get to this place where you assume the inductive hypothesis, right? And then you go to the k plus first step, and that's what this thing is. But then we actually want to be able to use our inductive hypothesis. So that would be like these guys, and you replace it with this thing, right? But then we have to make our stuff, which is not that pretty, look like this, but with k plus 1s. So k plus 1 times 3 times k plus 1 minus 1 all over 2. Right? We need to replace these guys with k plus 1s, which is gross. Like this would be where you like go off to the side and do some scratch work and figure it out. But like that this is that. The 3K plus 2 is 3K plus 1 minus. Right. Yeah, you should have done this. Yeah. You want it to be obvious to your reader if they were just looking from the statement of the thing you're verifying to your like last line of your proof. Do those match? Oh yeah, they do. Okay. Does that make sense? Yes?
Oh, that's why you're saying Stratford would be here.
I mean, look, these are my things. There's no Stratford, right? Yeah, if you're writing a formal, like if you're writing a paper, you turn in a rough draft just for like funsies, but like you're actually graded on your paper, right? Or you should be. Like I'm grading your final draft. I'm not even looking at your scratch. Yeah, I wouldn't care if you didn't turn that in at all. Yeah. Okay. This one y'all actually did quite well on. I was very impressed. I don't know if it was exactly like something we did in class or not, but I was very impressed by your, if it was creativity or just copying what we did before, but like doing that with like math part to make this work. Y'all did a great job.
I think we did something.
Yeah.
The idea was there,
Right.
whether it's
Right. And then the same thing with this one. Yeah. Again, y'all did this thing where you got to like here maybe and stopped, or maybe here and stopped. I don't know. But making sure it looks like K plus 1 plus 2. You know what I'm saying? Y'all see do you see the thing there? Like a lot of you stopped at this step. But really, to make it look like the original, we got to make that look like K plus 1 plus 2 factorial. Yes? Are we following, sort of?
oh, okay.
Yeah.
I think so.
Mhm. You can do anything there that you want that gets you where you need to go that doesn't break the inequality. So because K is bigger than or equal to 1, I know that this is true, that that's bigger. And getting bigger is fine and not going to break the, yeah. Yeah.
So you work from the one to the unless you did something wrong, you want to get
Reverse the
reverse the stuff.
Yep. In the summation ones, that's not the same on like these ones. That's not.
I stopped.
Right. That's a different kind of question. The thing that you want to do is to make your, when you get to your, okay, all right. When you get like done, this should match this with K plus 1s instead of ends. The bottom thing, the very end, should match the statement, but with K plus 1s instead of ends.
Okay.
So I guess, yes, you probably wrote that down and you want to show, I don't know. Yes? Okay. Again, this one was very good. I thought y'all did great with that. Yet this is the part where I'm like really glad that y'all separated this stuff. You didn't start out saying 3 to the 7th is less than 7 factorial. You're not, that's not the way you're trying to show. You won't do that. But y'all did, y'all separated them well. Like you were saying. Oh heavens no. I don't know what 3 to the 7th is, and yeah, no. If I did, y'all could just ask me and I would do it in my phone and tell you. Yeah. If there's an arithmetic question you have on your test on Thursday, just ask me.
Unless it's obvious.
Unless it's the like the math that you're supposed to be doing like from here. I'm not gonna tell you that. I noticed that. I don't think you're the only person. Can you what? Sure. Yeah. I counted all 4 on your homework because I didn't. The first time I let it go, I was like, oh, that's just a mistake. And then I saw it again. I was like, I can't let it go twice. Okay, so I think overall that was good, and it was probably good that you guys have had a chance now. We've had a chance to talk about it, and hopefully you can fix some of those issues, and we'll continue to work through that today with the strong induction examples that everybody okay? Yes. Now your homework that is due on Thursday, homework number 10, is 6 questions now. Yes? I think it's the 5 original ones and then plus the 1 extra from homework 9 that we were not able to do yet. Yeah? Now, that is going to be a completion grade. You will turn it in when you get here on Thursday. The point of the homework is to prepare you for the test, so doing it after the test is not what I'm looking for. Do you understand? You're going to do it before the test on Thursday, and you're going to hand it to me when you walk in the room or have emailed it to me already. Do we understand? I'm not going to grade it except to check that you did it, because I'm going to actually grade the questions on your test. Are we good? But if you have questions, what should you do? You should ask me, and I will help you. Yeah? Okay. Yes, sir. I just showed you all of the answers, so no. Maybe for half credit. Because nobody missed more points than that. So yes, half credit you can. Okay. So we're gonna do strong induction then now. Are we good? Does anybody have any questions? Don't be sorry. You raised your hand. I was ready for you to talk to me, Marina. What is your question? They do. Yep. The book is very confusing in the way, I think the book is really confusing in the way that they do induction proofs. The PK and PK plus 1 is like, what is even happening? I hate the way the textbook does it. I'm sorry about that, because that is resource that you should be able to have and use. But I think the way that they do it is confusing, and it doesn't read well either. It's very, I don't know, convoluted. So yeah, the format is the same, and I'm fine with y'all. Like Ruth asked me this earlier, because you have a note card for Thursday, but you can't have proofs on the note card. So, but you could have that, like the like bulleted list of like, we need to do the base case, we need to prove it for PK, or assume it works for PK, show for PK plus 1. So it's like, P, why is it even there? Show like for it works for n equal to k. And then consider, like, I think instead of doing the like p's, you could just say consider when n equals k plus 1, something like that, because I think that reads a whole lot better. And like your proof read like a textbook is like as explaining the process, and that's not how a proof should read. Do you know what I mean? The textbook should do that, but it shouldn't do that in the middle of the proof. I don't know. Do you know what I mean? Okay. I didn't count off points for that, did I? I just said I don't like the way this reads. Okay, good. Yeah. I think because you're looking for those transitional things, so I think saying like, consider, let's assume this works when n equals k. So we have this. Now let's look at when n equals k plus 1. I think that's a good way to do it. Okay. I got real lost on one of yours, Marina, because you were doing your ones the way that you write ones, which is fine if they're written well. But sometimes that little hat drags really low, and I was like, what the heck is this number? Is this a letter? It's like, is this an A? Where is this coming from? I was so confused. So I was like, oh, it all makes sense. It is a 1. I was also grading it while I was giving you a test, and I was so confused about a lot of things. Okay, on Thursday of last week, golly, which feels like it was an eternity ago, we did our only strong induction example. Today we're going to do more of that. So remember with regular induction, you show the base case, you assume it works when n equals k, and then you use that for some k. And then you use that to show that it works when n equals k plus 1. Now, strong induction, you do the base case or cases, and then you assume it works for all I up to k. Am I doing this right for you? This way. For all i's from your base case up to some number k. So you assume it works for all of them. And then you use all of that to show that it works for the k plus first step, or it works when n equals k plus 1. We good? So for strong induction, you need more than just the domino before it to have fallen. Yeah? Does that make sense? Yes? You need all the dominoes up to the domino you're trying to show have fallen. For strong induction, you get to assume that they have all fallen. For regular induction, you assume that for some k, that domino fell. And then you show that since the k domino fell, the k plus first one will also fall. But for strong induction, you need all of the ones up to k have fallen. And then to use all of them to show that the k plus first domino also falls. You have this blank look on your face like that didn't make any sense. Okay. What part do you not understand? Help me help you.
I get that in induction is you get on the ladder and then if you're wherever you are, you can get to it. I get that.
Mhm.
But for strong induction, not in relation to induction.
So for strong induction, let's use the ladder analogy since that's the one you get for regular induction. So for strong induction, the ladder analogy is like you can get on a ladder and maybe you can get on the first couple steps of the ladder. And then think about like, I don't know, I'm thinking about like a chimney sweep, like Mary Poppins, the like going up and down the ladder. So like for strong induction, it's saying that like we're assuming that we have gotten to all of the ladder rungs up to this particular one.
Okay.
And so for something like that homework question that we haven't done yet, things that are defined recursively, which we're going to get to, but like this thing, you see how the nth step depends on the n minus 2 and n minus 1. This is the previous ladder rung, and the ladder rung is 2 away. So you've got to assume all the way up to the one you're on, because we're going to have to step back, use this and this to get this. Yeah.
Okay.
So strong induction is you have to assume more stuff, right?
So we're assuming
So you've gotten to all of the ladder
that we
rungs.
have gotten all of them except for
You're going to use all of them to get to the next one. So that's what we did on this proof that any integer greater than 1 can be written as a product of primes. We got to this place where, so greater than 1, we let n be 2 for the base case. N is already prime, so it's written as product of primes, so we're done. And then we suppose for all integers I up to the kth, and you see that the purple highlighted part, so that's that we're all ladder rungs up to the kth one, it works. Up to and including the kth one, it works. So that all of those numbers I can be written as product of primes. And then we look at the k plus first integer. And now we're going to use 2 of the ladder rungs that have already happened. Sorry, not that. We're going to use 2 ladder rungs that we've already stepped on to prove it for the k plus first step.
I guess it's easy.
Here is one now. You see how we used this m and this n? Well, both of these we need. These are the 2 ladder rungs we needed. We didn't just need 1 ladder rung to prove that we needed 2. And that's where the strong induction thing came from. And why we need strong induction and not just regular induction. We both ladder rungs both to launch us to the Yep. Okay. We'll do more examples and hopefully it'll make more sense, but that's sort of the idea of what's going on. Now this example is convoluted, so I'm not sure it'll help. It's a good example. it's a good example. Let's do it. So we are going to prove that every amount of postage that is 12 cents or more can be formed using just a 4-cent stamp or just 4-cent stamps and 5-cent stamps. Now, here's my thought. When I see this problem, I think just pick a number for postage, take off, if it's one more, you know, to get to the K plus first one, take off the 4-cent stamp and put on another 5-cent stamp. You tracking what I'm saying? Are you? Let's say we're on 16 and I need to get 17 cents. I have 4-cent stamps. You with me? What? Well, if I just take off one of them and put on a 5-cent stamp, boom, I've got 17 cents, right? So why do I need strong induction? And that's a valid question. What if I have 15 cents and need to get to 16? Can I take off a 4-cent stamp and put on a 5-cent stamp? I don't, and that's a problem. Yeah, because I can't just back up one step. I'm going to have to back up several steps when I did have a 4-cent stamp and take it off and put a 5-cent stamp on. Yeah. We'd have to go all the way back to like 12 and take off one of those and put on a, what was I trying to get to? I don't even know. Okay. 15 to 16. Yeah. But to get to 16, I can't take off a 5-cent stamp and put on the 4-cent stamp. That doesn't help, right? Yeah. We're going to have to back up more. We're going to back up 3 or 4 to then do it. But let's actually like work it out. We can't. That's what I'm saying. This is what I'm saying. This is why we need strong induction, because we need to know that we could have gotten to everyone before that, and we're going to back up to one that does have a 4-cent stamp and take it off. I don't know. Yeah. Sure. Yes. Yeah. And then back up to a place where you can move that way again. Yeah. Mm-hmm. Yes. Mm-hmm. Here's what we're proving, that 4a plus 5b is equal to n, that we can write any integer greater than 12 as 4a plus 5b, where a and b are integers, or are natural numbers, because we don't want to have our whole numbers. So for all n and z, when n is greater than or equal to 12, we can write n as 4a plus 5b. Okay, so we will prove by strong induction that there exists no, I cannot. I will in a minute probably, but I'm going to try to write the proof first. Do you want me to scoot this over so we can? Unfortunately. This was a proof where it was just exploratory, so I could show it to you. And then we were going to work on it. What is it? Here's mine, but I did write pretty good. Okay, so base case n equals 12. Here's the thing is I don't really know how many base cases I might need, but when n equals 12, we can obviously do this, right? We would have 4 times 3 plus 5 times 0 equals 12. Let's just like practice some. Can we do it for n equals 13? What would we do here? Yeah, so we do 4 times 2 plus 5 times 1, and that's 13. How would we do n equals 14? How would we do n equals 15? 3 5. Okay, so I think this is going to help us. This actually will help us get a like pattern here. But do you see what's going on? We have the multiple of 4 and the multiple of 5. And if we're doing this thing where you're like, you know, like the number of forcing stamps is decreasing, well, the number of 5 stamps is growing, and then it's going to go backwards. Yeah. So the idea here is that at any step in here, we want to be able to like, we're gonna like back all the way up to here, and then we're gonna add rather than taking stamps away. Because if we're taking stamps away, then we can't ensure that we have it. We haven't taken away stamps, it doesn't exist. So but I think establishing all of those, we hit both places where you have no 5-cent stamps and no 4-cent stamps. And so we're going to be able to work with this to like do a thing. This is bizarre. And I'm showing you this again as an exploratory thing. And then you have the opportunity to also do this on your homework. And probably will have the opportunity to show off how much you've learned on the exam on Thursday. Non-negative has 2 ends right there. Okay, I'm just setting up proof stuff so far, and I'm going to do those as my base cases. So there exist non-negative integers a and b and such that n is equal to 4a plus 5b for all integers n greater than or equal to 12. And we're going to look at those four things we just did. So we have 12. I should start with 12. 12 is equal to 4 times 3 plus 5 times 0. 13 is 4 times 2 plus 5 times 1. 14 is 4 times 1 plus 5 times 2. And 15 is 4 times 0 plus 5 times 2. And we're going to say, so the base case is whole. Now, I know that you look at this and you think, like, how do I know that I need to do that many? And I'm going to show you in a minute why I think that you do. I think you can use this to then do this over and over again in a way that can help. Okay. Well, good. So, for the inductive hypothesis, remember this is strong induction. We are going to assume for all I am starting at my last base case. So 15 is less than or equal to I, which is less than or equal to K. Okay, so we're assuming this works for all of those. So I is equal to 4A plus 5B for some A, B, and Z non-negative. Okay, so what we have done so far, you guys, is establish that we can not only get on the ladder, but we can take a few steps on the ladder, right? And we are also assuming that from 15 all the way up to some integer K, that we can write that integer as 4 times a non-negative integer plus 5 times a non-negative integer. Good? Yes? So, what we need to do is show that we can write what as 4A plus 5. What's the inductive step? Not I plus 1, but K plus 1. Yes. Right? Because that I goes all the way up, those I's go all the way up to K. Yeah? So K is the last of all of the I's that this works for. We want to show that it works for K plus 1. I'll go back to my scratch work now and do some stuff. So, hypothesis, we have 15 less than or equal to I less than or equal to K, that I is equal to 4A plus 5B for non-negative integers A and B. What we want to show is that K plus 1 is equal to 4. That's not a 4. That isn't either. Is equal to 4 times an integer plus 5 times an integer. Non-negative still. Okay, so I mentioned that for strong induction, and for this proof in particular, we need more than just what's happening at the K step, right? Because don't write this down, this is an aside. If I substitute in here 4A plus 5B plus 1, using, the inductive hypothesis here, right? If I do that, I am stuck. Yeah? I can't, what am I going to do with that? I can't really do anything with that. Are you with me? I would really like for this number that I'm adding on to be a 4 or a 5, so that I can group it with the stuff that's attached to 4 or the stuff that's attached to 5. Does that make sense? I would really like for that thing I'm adding on to be a multiple of 4 or a multiple of 5, because then I can group it with A or I can group it with B, and I'm good to go. So what we're going to do I subtracted 3 and I added 3, so I have done nothing except give myself a multiple of 4. Yeah?
Oh, okay, that's what I'm saying. Somehow
I creatively added 0 so that I could Now, this is allowed because I'm on the case that my inductive hypothesis says that all the way up to K, this works. I'm backing up 3 steps from K, but I can do that because I proved it for how many base cases? 4, right? So if I was starting on 15, which is what I said I could start on, right? If I'm starting on 15 and I can back up to here, and I already proved it works. And that's this is the smallest thing that I can start with because that's what I made I start with. We good?
So why do you want
Why did I want which part?
the it's like
Mhm.
15?
Because I knew I was going to back up 3 steps. So I needed to establish it in a way that allowed me to do that. I know that. But you would when you're doing your stuff later. And now you've seen it happen. And so you know how to expect it, anticipate it, and do it again. Yeah. You need a multiple of 4 or you need a multiple of 5. I could have also done K minus 4 here, right? I can do K minus 4 plus 1, and then I have a 5 here, which is good. However, I would need to do a 16 so that I could back all the way up 4 steps and still be good to go, staying within greater than or equal to 12. Does that make sense? So my n starts at 12. That's the smallest number this works for. So I don't want to start my i's at 12 because I'm going to back up my k's. I can't back up my k's smaller than that. Yeah. And so I'm looking at this and I have I'm looking at this is K minus 3 plus 4. And I know that this is equal to 4A plus 5B plus 4. And this is because K minus 3 is an I. Right? It's sitting between 15 and, well, it's either a base case or it is sitting between 15 and I. Is that making sense? Yes? And again, this is for A and B in xenon neg. Or Z greater than or equal to 0. And so this is 4 times A plus 1, right? Plus 5B. No, because natural numbers don't include 0, and we need 0.
Okay.
Right, we need 0 because there are multiples of 5 and multiples of 4 that are not multiples of both, so you need to have 0. That A or B could be 0. So since A plus 1 and B are elements in xenon neg, we have K plus 1 is equal to 4 times A plus 1. I don't know. I think we can just say, since that is true, we're done. Since A plus 1 and B are in xenon neg, we have shown there exist non-negative integers. I'm going to call them x and y, such that n is equal to 4x plus 5y for all in greater than or equal to 12. Mm-hmm. Yeah, if you were doing it for 5, you would go K minus 4 plus 4 plus 1, right? And if you got the K minus 4, you would need to start your K's at 16 so that you could back up and not go smaller than 12. Does that make sense? You would start your I's at 13, at 16, so that the smallest it could go. So like right now, the smallest I is 15. So the smallest that K minus 3 could be is 12. Right? Which is fine. But if I did k minus 4 with only these base cases, I can't back up 4 because I don't know anything about it. I wouldn't be able to say this part if I hadn't also proven the 16 and started
So
there.
is that why you said you didn't necessarily know how many bases?
Yeah, you don't know. I mean, if you have a recursively defined sequence, which we'll talk about in a minute, you know how many base cases you need because you need enough to establish the property. But like here, it is sort of exploratory in nature. Like you've got to, I think on your homework, I've seen this question recently, so it's either on your homework or your test, but it's doing 2a plus 3b. So you have to get a plus 2 or a plus 3. So you're going to do a minus 1 plus 1 or a minus 2 plus 2 to get a plus 3. We tracking?
I've seen that before, so like, that's what I was
Yeah, right. You're creatively adding a 0 so that you can like split things up and use them in a particular way. And this particular way is so that I can back up and use the fact that k minus 3 can be written as a 4 times a thing plus 5 times a thing.
valid.
Oh, yes, absolutely. So this one doesn't, I don't actually need several ladder rungs. I just need one. But the problem is that I don't need the one that's right behind me. I need the one that's several behind me. And that's why we need strong induction. Yeah. Because regular induction only means I have the ladder rung that's right behind me or right underneath where I am or what I'm trying to prove. And that wouldn't help me here. On all of them. It would on some of them, but not all. Okay. We good? Questions, comments, anything you got? No? Okay. Like I said, I think there's one of these on your homework. I should probably check. But I would. It's a good question. Okay. So the other time where this is useful is when you have sequences that are defined recursively. So that means that like, so that all of the, here are the things. Look at these. These things, you have a sub n is 1 over n, right? So the nth term in this sequence is just 1 over n. You're looking at 1 over 2 for n equals 2, or 1 over 17 for n equals 17, right? All it depends on is knowing n. You get what I'm saying? That second one, to figure out that term in the sequence, all you need to do is know what n is. That's it. Same with the next one. All we need to know is what n is. But sometimes sequences aren't defined like that. They are defined recursively, which means it's given in terms of one or more of the terms in the sequence. So the Fibonacci sequence is a great example of this, right? So the Fibonacci sequence is a sequence that takes the first two numbers are 0 and 1, and all of the rest of them are the sum of the two previous ones. So F2 is 0 plus 1, F3 is 1 plus 1. I can't do this in my head. F4 is 1 plus 2. I think I'm doing this right. Okay, y'all are with me? Fibonacci is familiar to you or no? You're not? Yes? No? Fibonacci sequence is like all over nature. Okay, so then when n equals 0, you're a 0. When n equals 1, you're 1. It starts out with this sort of thing. And then the next one is the sum of the previous two. So 0 and 1 is 1. 1 and 1 is 2. 1 and 2 is 3. 2 and 3 is 5. 3 and 5 is 8. 8 and 5 is 13. 13 and 8 is 21. I can't add anymore, so we're going to stop. Yeah, it is. There are so many mathematicians who really dig in so hard on Fibonacci sequence stuff in nature, and like it's great, and like the golden ratio, and like it's accessible. So like I get it. Like anytime I'm at a conference and I see a talk on the golden ratio or Fibonacci sequence, I'm like, pass, hard pass. Whatever. It's been tainted, I guess. Anyway, the Fibonacci sequence is wonderful. But yeah, it's found all over nature. Intentional design. This is a thing where people use like math and science and nature to prove that God created the universe. Yes. And like for this stuff to happen everywhere, the probability that that just happens by chance is harder to believe than that it was created by someone because it's so prevalent. Oh, I hadn't heard that. So there are like spirals in like pine cones. You can count pine cone spirals. They're all Fibonacci numbers. Petals in a flower. Just Google it. There are all kinds of things. The golden ratio in art. These things, the ratios of these make golden ratio. It's whatever. It's all over the place. But anyway, the point here is that if we were the term you're on, the nth term in the sequence, it depends on the previous two. So if we were trying to prove something inductively here, we need at least the two ladder rungs behind us, right? So you need strong induction here because you have to know about the two behind you to make to prove something about the one that you're on. Does that make sense? Yes. This one here, number 2, it only depends on the previous term, but you see it's defined in terms of n minus the n minus first term, so it depends on the previous term. So like A1 is 2, A2 is going to be A1 squared, so you're looking at 4. A3 is A2 squared, so that's 16. A4 is A3 squared, 256. That would be a regular induction, yeah. Because, and that's a great question, Whitney, like the first one, you need 2 ladder rungs behind you, so you need strong induction. On number 2, you don't need strong induction because it's just the one. The sequence is still defined recursively, but all you need is the previous step to do it. Number 3, you can see there that depends on the 2 previous terms, right? It depends on the n minus 1 and the n minus 2 term when you're on the nth. Yeah, it's not always the very last 2, no. Sometimes it goes like, it'll use the n minus 4 or, n minus second or whatever. It doesn't matter to y'all what those terms are in the sequence. You don't care, do you? You can plug in numbers and figure them out later if you're interested. Yes? My notes have me very overwhelmed for this next bit. It's a lot of writing. Why? Oh, it's options. Many options for a proof. We're not going to do many options. We're just going to do one. Okay, so strong induction proofs with sequences. This is what was on that homework that y'all got, the problem that you got to skip to do on this next homework, where you have a sequence given to you by these things. Now, the hardest thing for students to do when they're doing this that I have found is knowing what you're assuming, what's the definition of the sequence, and what are you trying to show. Okay, so this sequence is defined by S1 is 1, S2 is 3, Sn is Sn minus 2 plus 2 times Sn minus 1. That's the definition of the sequence. We don't have to prove anything with that. That's the definition of the sequence, right? The thing we're trying to prove is that Sn is odd. That's the thing we need to prove. So we are going to prove that Sn is equal to 2 times an integer plus 1 for all n greater than or equal to 1. So I ask you, what do we know and what do we get to show? So here's what we know. Yes, S1 is 1. You didn't mention this, but this works too. And also that Sn is Sn minus 2 plus 2 times Sn minus 1. Those three things we know. Yeah? Now, what are we trying to show? That Sn is equal to 2 times an integer plus 1 for all n greater than or equal to 1. So your base case, or case is, what do you think that we need to do? How many base cases do you think we need? 3. For the two terms in the sequence that are given to you, and then to establish that it works with the definition of the other terms in the sequence. We tracking that? So for n equals 1, n equals 2, and then the first time that we actually have to find the term in the sequence. Yeah? Does that make sense? Yes or no? Well, I have 1 and a 2 here I have to prove. And then I need to establish that it works whenever I plug those into there. Yeah. If this was given, the one on your homework, how many base cases? Well, let's look at the next one on here. How many base cases do you need here? 4. You need the 3 given entries in the sequence. You need to show it works for them, and then show it works for the definition of the sequence with those things plugged in.
So whatever's there,
However many this needs to backtrack plus 1. Yeah.
even though that it's 3, the backtracking,
Because it backtracks 3 because it's defined to be n minus 3. This thing depends on the 3 previous terms, so I need to prove it for at least those 3 plus this definition thing, because we have like these don't fit this necessarily. That's kind of the point. So you have to do it for those and for the like actual definition of the sequence once it starts working. What? Wait, what? What would be n plus 1?
so you show it for those things and then one more after that.
What is your n, Ruth? I mean, yes, but what is n? Yes, it is.
Arbitrary number.
But in this problem, so it's not arbitrary. Good. You need to show it for all of the things given to you plus the definition of the sequence. So that's a 1, 2, 3, and a 4. No. Yeah. But this is like, yeah. Why? Because you just need the previous step, which is what regular induction gives you. Yeah. Y'all, if this was an n minus 2, we would need strong induction. Tracking that? Okay, let's back up and let's do the thing. All right, so when n equals, when n is equal, well, our base case is we're going to show it works for n equals 1, n equals 2, and n equals 3. Well, 1 is obviously, 1 and 3 are both odd, so you're done. When n equals 3, what is s sub 3? And altogether, they said, maybe we did need to plug in those numbers and make sure we know how to read a sequence. What is s sub 3? Yeah, Charlotte, you said 7, right? Yes, and yes. Yeah, it's S1, because that's S3 minus 2. right? S sub 3 minus 2. Plugging in right here. A 3, a 3 minus 2, a 3 minus 1. Yeah? No? Yes? Yes? We're taking this thing, this is the definition. Ooh, let's put that in a different color. This is the definition of the sequence. We're on the third term in the sequence. So S sub 3 is S sub 3 minus 2. That's S sub 1. Plus 2 times S sub 3 minus 1. That's S sub 2. And Charlotte said that's 7 because she is taking 1 and 2 times 3, which is 7. S sub 2 was given also to be 3, and S sub 1 is given to be 1, right? So we, yes? Yeah. Are we okay? Yeah? All right, so we have that it works for all of our base cases. Now, what is our inductive hypothesis? What do we get to assume? That what? What do we get to assume about those? That's the definition. We know they equal that. We don't have to assume that. We know that. That's the definition. What are we trying to show? Right. It's specifically that S sub I is odd for all of these i's. Y'all get what's happening? For all of the i's up to k, S sub I is odd. So S sub I equals 2 times some integer plus 1. Okay, I'm gonna write a proof now because I don't have any more space for my scratch work. So, oh well. So we are gonna let S sub n be the sequence defined by S sub 1 equals 1, S sub 2 equals 3, and S sub n is equal to S sub n minus 2 plus 2 times S sub n minus 1. We will show that Sn is odd for all n greater than or equal to 1. For the base cases, consider n equal to 1, 2, and 3. Notice S sub 1 equals 1. S sub 2 equals 3. And S sub 3 is equal to 7, which are all odd. Thus, the base cases hold. For the inductive hypothesis, assume for all integers I with 3 less than or equal to I less than or equal to k, okay, so here also, that S sub I is odd. Okay, so am I want to show step? Maybe I should have done this. I'm gonna back up over there and to do this, but in my want to show step, I'm trying to show this works for the k plus first step, right? I'm trying to show that s sub k plus 1 is odd. Yeah. That's what we're gonna do right now. We're gonna consider s sub k plus 1. What do I know about s sub k plus 1? What? Where? Where is m plus n? Where? I've graded y'all's homework. Probably Kool-Aid. Well, I'm glad to show you something new.
I knew what it was.
So what do we know about s sub k plus 1?
Sorry, I didn't get that. Could you
Siri, they don't get it either. What is s sub k plus 1? No.
Here's what I found.
Good Lord. What do we know?
S sub n.
Okay, what does s sub k plus 1 equal? Yes. Charlotte, where in the world did you get that? You replace the n with a k plus 1. Yeah, that's the definition of the k plus first entry in the sequence, right? This is the definition of the sequence. So all I have to do is plug in that k plus 1 for n, and I have the definition of the sequence. Yeah, that's it. Charlotte went ahead and, k plus 1 minus 2 is k minus 1. And then k plus 1 minus 1 is just k, right? What do we know now? What do you know about s sub k minus 1? Logan, what do you know about s sub k minus 1? It's odd. Why? Because it's an I. Yeah? This k minus 1's in there. Yeah? What is also in there? That. So I know that both of those are odd. Yeah? Okay, so I'm looking at an odd plus an even, which is odd. But, so this is 2L plus 1, and this is 2 times 2M plus 1 for L and M and Z. And that's by the inductive hypothesis. Is everybody okay with that? Well, and I don't know if this is obvious, but hopefully it is. This is L plus 2M plus 1 plus 1 out here. I I just pushed that 2L, well, the L into the parentheses with the 2M plus 1, you know? I already had a 2 factored out. This, oh, this and this. I just decided to factor that 2 away from the L2 and scoot it in there. Because now I'm done. L plus 2M plus 1 is an integer. K plus 1 is odd. We have shown Sn is odd for all n greater than or equal to 1. How are we doing? Okay? Yeah? Okay. Yeah. The knowing what you know, what you're trying to show matters. Being able to like, if there's a lot of stuff floating around, all of the stuff itself is not that hard. But when you mix it all together, it can get jumbled. So let's do perhaps one more before we walk out of here today, and I will post these other two. Yeah? We'll just ignore 5.7's existence. Cool. So on this one we have A1 is 1, A2 is 2, and AN is defined this way. How many base cases do we need, Ruth? 3. Good. I'm not writing scratch work, please just ignore that. So we're gonna let A sub n be the sequence. My iPad is dying. Be the sequence defined by A1 equals 1, A2 equals 2, and AN equals 2. I don't have room to write that right there. AN minus 2 plus AN minus 1. What are we trying to show? Yep. We're trying to show that A sub n, every entry in the sequence is less than or equal to 2 to the n. Okay, so for the base cases, remember we're going to prove this for 3 things. For n equals to 1, 2, and 3. Notice A sub 1 is 1, and 1 is less than 2 to the first. A sub 2 is 2, and 2 is less than 2 squared. And maybe I have semicolons here. I don't know what's happening. So finally, the English here is lacking. It's okay. A sub 3 is equal to 2 times 2 plus 1, which is 5. Obviously, 5 is less than 2 cubed. Huh? What? Right.
Oh, okay.
Yes. Good. You got it. Yes, obviously 5 is less than 2 cubed because 2 cubed is 8. Okay. So the base case is hold. Now for the inductive hypothesis, What do we want to assume?
I didn't understand that.
Me neither. Good. Perfect. So. I mean, not. It's obviously an integer, whatever. Okay. We're going to consider a sub k plus 1. What is a sub k plus 1 equal? Which is k minus 1. I'm with you. Yes. Plus 1 minus 1, so just k. Okay. What do we know? A sub I is less than 2 to the I for all I up to k, and including k. So that's less than 2 to the k plus 1, and this is less than 2 to the k. Yeah. What are we actually trying to show? What do we want to get? Let me not write that down. What are we trying to show? That a sub k plus 1 is less than or equal to 2 to the k plus 1. We're tracking? Yeah, that's this thing with k's instead. Alrighty. This is equal to 2 to the k. This is 2 to the k. Wow. Would you make a louder entrance? I don't think so. This, no, I don't think so. This is 2 times 2 to the k, which is 2 to the k plus 1. Hi, Bryson. Uh-huh. Yeah. Do you track what's happening or no? Or where did we lose you? Good. No coins involved. Hey, come on in. Yeah, we did it. This is the and I've kept you long enough. You would say we have shown. Don't do a box while you say anything. We have shown. A sub n is less than or equal to 2 to the n for all n greater than or equal to 1. I mean, that's a greater than sign. And then there's a box. Uh-huh. And I will post the other two ASAP, and we will ignore that being said. Yeah. No, so we have to do a sub. We need to probably do one subset proof on this one. So we didn't do a subset proof on the other test. Yeah. No. One subset proof you can count on. Hi, Mia. One subset proof, and then guys, 5.7 is just finding the sequence. It's fine. We don't know. Go. A little bit. Just doing my best. Okie dokie. You're good, Charlotte. I'm ready. Well, see, you came in late. Were you done with it before you walked in the room?
Yeah, I actually finished it last night and I forgot to send it. Oh yeah.
But you didn't add